We invite every delegate on site and online to join us here for two outstanding keynote addresses. To guide the session, may we now invite to the stage our session moderator, Dr. Sabdo Utomo, PhD. Please come forward to the stage. Dr. Sabdo Utomo, PhD. He is a researcher at the Research Center for Smart Mechatronics, BRIN, with expertise in computer vision, artificial intelligence, trustworthy AI, and smart farming application. He holds a PhD in ambient intelligence and smart system from National Chung Cheng University, Taiwan, and has over 20 international publications.
Dr. Utomo, the floor is yours.
Thank you, Anas and Amarah. Okay. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to check if Dr. Francisco, can you hear my voice?
Hi, hello. Yes, I can hear.
Okay, cool. That's great. Okay. Let me give a brief overview of this session. We will have two distinguished speakers from Huawei Hong Kong and from the Institute Technology 10 November Surabaya. First speaker is Dr. Francesco Cursi. He is a senior research engineer from Huawei Hong Kong. And then the second speaker is Professor Insinyur. He is a lecturer and head of Coastal and Port Infrastructure Laboratory, ITS Surabaya. Okay. It's very honor for me to lead this session today. As the Master of Ceremony introduced myself, I'm Sabdo Utomo. And today, I would like to introduce our first speaker. Maybe you can, yeah, this is. Our first speaker is Dr. Francesco Cursi. He holds his PhD from the Imperial College, which one is one of the best university in the world. And then his research focus on machine learning and robotic control for tendon driver surgical robot. He has since worked as algorithm engineer in the computer vision for manufacturing, and he is now senior research engineer at Huawei in Hong Kong. Okay. He earned his master degree from Sapienza University of Rome and New York University. It's very, very good background, right? And today he will take us through the fascinating question. As AI advance, how robot transform from the pre-program into the autonomous agent that can understand human instruction and adapt to unstructured environment. Okay. Dr. Francesco, if I give you 25 minutes, is that enough for you?
I'll try. Yeah, should be fine. Yes.
35 minutes. Okay, right?
Yeah.
Okay. Now, please welcome Dr. Francesco Cursi. Time is yours. Okay.
Thank you. Okay, let me. So can you see my screen?
Yes.
Okay. I'll go ahead. So yeah, thanks first of all for the invitation. I hope it will be an interesting topic. Sorry, 1 second. Okay. So basically, yeah, as mentioned, so my speech is a bit high level talk about how robotics have changed over time. So going from very pre-programmable to more autonomous systems. So as mentioned, yeah, I mean, my background dates back to, I mean, I've been in robotics for a bit of time. So ever since I started, my bachelor and master in Sapienza, so I'm Italian, so I studied in Italy, and then I moved to New York for a master. Then I went to an internship at the Italian Institute of Technology, where I was working on force torque sensors for humanoids in the humanoid and human-centered lab under Nikos Zagaragis. And then I went for a PhD, so Imperial College London. I was between Hamlin Center and the Robot Intelligence Lab, where my work was about machine learning and optical control for autonomous robotic surgery. And then after a PhD, so I moved to Hong Kong, and mostly I've been working for Huawei, where I've been a senior researcher in robotics and embodied AI. And I've been working on different topics actually in robotics, so like reinforcement learning for table tennis, foundation models, and more recently, VLAs. So basically, the presentation, as I mentioned, is going to be a little bit of history of robotics, so how AI has been affecting and influencing robotics more recently. And then this new concept of VLA, so visual language action models, and also word models and video generative models for robotics. And then also go a little bit through logo manipulation and humanoids, which have been very popular recently. And then some open challenges and future directions. So basically, I mean, before, like maybe 20 years ago, so I mean, even 15 years ago, robots were still mostly pre-programmed. So that means that, especially in manufacturing and so on, there were very fixed pipelines. So there had to be like an engineer who would uh, program every almost motion robot, and also robots generally were very confined to specific areas of the workplace, where everything, as I mentioned, was very structured and, very specific. Then in the early 2000s, there was this new concept of collaborative robots, also named as cobots, which were a bit more human friendly. So humans could get closer to these robots because there's some force control, so impedance and admittance control, which allowed the human to actually move the robot itself. And so they could sort of teach. It was not really teaching, it was mostly just recording some trajectories, and then the robot was able to replicate these trajectories. Then AI and computer vision started to be integrated more into robotics. So it started, as I mentioned, so mostly with computer vision and some more perception. So in that case, it was easier to identify objects and a bit more less structured situations. And then eventually, like in 2022 and so on, so AI became a major important component in robotics. So with these visual language models, word action models, and so on. And the goal is to make robots much more autonomous, so that they rely much less on pre-programmed behaviors, and they are able to reason more and eventually generalize to different scenarios and tasks. So basically, what happened is that AI for sure had a big boom, like especially in 2017, which was a very, very important moment also for the broader field of AI. There was which is called attention is all you need, which was a very important breakthrough, especially for natural language processing, which was when they came out with this transformer architecture. So transformer is basically at the foundation of LLMs. So as like ChatGPT, Gemini, they're all LLMs. And these LLMs, I mean, the good thing of LLMs is that they were able to, thanks to this transformer architecture, they were trained and then were able to understand human language. They were able also to learn from very few examples, given by human, and then also generate text based on following certain instructions from the human. And then given the capabilities of these LLMs, so the technology moved on to what's called multimodal LLMs or visual language models. So instead of only using language, so at the very beginning, LLMs, I mean, it's just text as input and text as output. And then so there were these additional breakthrough where instead of only text, so also images could be input to the model. And so these models nowadays are able to also understand images, so do some spatial vision question answering. So if you pass an image to ChatGPT, Gemini, all this model, and you ask question about this image, so the model is able to understand what happens, understand what you are asking, and eventually produce some text as output. The thing is, so in robotics, I mean, only text is not, so important because, I mean, robots actually need to move around. So in robotics, there was this shift by making these new models called visual language action models. So visual language action models, basically, they have similar ideas to LLMs and VLMs. So basically, you have this is an example from this Google model called RT2. So you have this transformer architecture that takes text, images, and then, as I mentioned, so instead of outputting this concept of imitation learning, so once you have these ground truth actions that you have collected from your data, so the model is trained to replicate these actions. And the major important factor is that, so by using these VLA, so there's no need for, as I mentioned before, like having structured and pre-programmed skills, let's say, because I mean, so this model by itself is able to understand what the human wants, how the robot should move given the current state, and what the robot should do in order to solve a task. So it's just one single model, which is a sort of robot brain, let's say. And then the idea is that ideally, if you collect enough data, so you are able, I mean, the robot is able to generalize to unseen objects, unseen tasks, and also unseen environments. But for sure, I mean, it comes with a lot of challenges. First of all, the data collection, then cross-embodiment, because ideally, I mean, you would like this model to be able to be used by different kinds of robots. And then the other important issue is for sure the real-time inference, because again, like LLMs, maybe they can take 1 second to generate text, but in robotics, actually, I mean, you want robot to act quite frequently, so it needs to be quite fast. So as I mentioned, so nowadays in robotics, there's this new concept of VLAs, but VLAs have had quite a bit of revolution, let's say, I mean, or changes over time. So one of the first approaches, which was a quite simple approach, was this approach of modular approaches, let's say. So there's this work from Google called Codex Policies and also ChatGPT for robotics from Microsoft, which basically was based on a very simple concept. So if LLMs are very good at understanding human language and also given a task, so LLMs and given also some skills, the LLMs are good at making a plan for how to solve this task. So why not directly leverage, LLMs and their capabilities to control robots? So basically, the idea was to have a large language model, which could be anything, as I mentioned, Gemini, GPT, whatever. You give to this model some additional information about some skills that the robot has as a form of API. For instance, grasp, move to, detect object, and so on. And then you give, your instruction. You can also use a VLM, so visual language model for success detection and also, object detection. And then you give this task, you pass the image, and then the LLM is able to understand how to decompose the task and how to plan the actions, for the robot to accomplish this task. So this was an example from Codex Policies. So as you can see, I mean, here they use this approach, and they ask the robot to put away the Coca-Cola can and the apple on the corresponding bins. So this is the only thing that they tell, this system. So then the robot has a camera. So because of the skills it has, it is able to understand what the Coca-Cola can is, where the bin is, how to get to the bin, how to navigate around. And then it's able to generally, perform this task quite well. And as I mentioned before, so basically it's the whole LLM that generates this code here on the left. And then once the code is generated, so it just runs on the robot, and the robot, acts and performs the task. So the advantage of this approach is that it's quite easy to implement because I mean it just takes some library of skills and an LLM. It's very human readable, so because you can understand each step of the plan, so what the robot is going to do. And generally it works also with any robot API. The main problems are basically two. So one is that first of all, so the LLM has no actual information of what the consequences of an action could be. And then the other thing is that for sure you need to have these manually defined skills, and these skills can be either pre-programmed by a human or learned through reinforcement learning or other approaches, but you need to have this skill defined. So in order to overcome these limitations, so then researchers started to focus more on this other strategy, monolithic transformers. Basically, the idea was, okay, I mean, if LLMs are based on transformers and they're able to produce text, so why not trying to use the same approach for robotics, but instead of producing sequences of language tokens, we train these models to produce sequences of action tokens. And some of the major works were these RT1, RT2, Octo, and OpenVLA from Google and so on. And basically, so as I mentioned, the idea is basically just like LLMs. You have one single transformer that processes images and text. So both images and text are tokenized by some encoders, like in this case, Dino and Siglip. And the text also is tokenized by some language tokenizer. And then all these tokens go in this OpenVLA, they go into a single LLM model, which in that case was Llama. And then in OpenVLA approach, so what they get is they train the model to output action tokens, but these action tokens are basically just sort of language. So this model was actually trained to output actions as language. And then these actions are detokenized and generate robot actions. So as you can see here, these are some examples. So again, like this model was trained on different tasks with large amount of data, and it was able to solve these tasks like just by giving an image and text. So the robot was able, for instance, here put eggplant into pot, was able to pick the put into the pot, and they show that compared to other approaches, so their model is able to generalize to different images and also have quite good language grounding. So basically, given the same image but different language instructions, for instance, on picking different objects from the same scene, so the robot and the policy is able to understand the human instruction, then complete the task. The main problem is that for sure, so you need to fine tune these models, and generally because it's already here 7 billion parameters, so it's quite decently big model. So generally you need quite a lot of data to train this model. And the other issue is that because you are fine tuning a pre-trained LLM or VLM with new data, so generally you have this catastrophic forgetting. So which causes generally loss of generalization to unseen tasks and so on. And generally was quite limited to quite simple tasks like just pick and placing. So after these challenges, so a major breakthrough came at the end of 2024 with Pi0, which is a new model architecture, new VLA architecture by physical intelligence. And this architecture is quite innovative because what they did was basically using a pre-trained VLM. So in that case, they used Gemma, but then have another additional transformer, which is an action expert. They interact with each other. But by having this what's called mixture of transformer architecture, they were able to preserve the knowledge of pre-trained VLMs because Gemma it was a pre-trained VLM on internet data. So it's a sort of Gemini. So it was able to understand, images and text from, internet data. So not specific to robotics. And then they made some additional improvements. So for instance, in Pine 0.5, and they added more reasoning. So just like what happens in LMs, so there was this introduction of chain of thought also in VLAs. And these models are generally trained on very large amount of data with additional tasks like visual question answering, object detection, trajectory prediction, and so on. And a similar approach is this one from embodied chain of thought, where the major improvement was, as I mentioned, so adding this chain of thought during the training on these VLAs. And basically, this is the architecture. So as I mentioned, so it was a new innovation in the field of VLAs. And as mentioned, so you have two experts. So the sort of understanding expert, which is, the VLM, and then the action expert, which accomplish two different tasks. So the VLM generally is for understanding language and, understanding the image. And then you have the action expert for action generation. And generally, so these models are pre-trained on, as I mentioned, lots of data, coming both from internet, but also, robot-specific data. And generally, so you have text and images, which again are tokenized. They go into the VLM. And then you have this other approach, which is called flow matching. So flow matching is also a technique coming from image generation, where in this case, in your action expert, you input robot state, so generally joint positions, and pure noise. And then this model is trained to denoise the noise. And then from just pure noise, it's able to reconstruct a sequence of robot actions. And then because it's basically transformers, so they also have this attention mechanism. So the noise tokens are able to, so the action expert is able to generate actions because these actions are able to attend to language and images. So by getting information from the language, from the image, so the model is able to predict future sequence of actions for the robot. And here it's their improvement on, by adding more and more reasoning. So this is the Pi 0.5 architecture. So basically what they did was, okay, the model didn't change. So the model architecture was still the same. So this VLM plus action expert. But as mentioned before, they added more, let's say, chain of thought and reasoning tasks. So this model is able to, like for instance, in this flow, so not only predicts action, but it's also able to, given a certain language instruction, to decompose this language instruction into subtasks. And it was also trained, actually pre-trained on object detection, so being able to detect objects from images, multimodal web data, so vision question answering, so just complete random questions on images and understanding these images and questions, and then for sure like on robot data. And what they show, for instance, in this video, they show that this robot was never trained on such scenario in such a room, but despite that, so because of the reasoning and the large amount of data they used, so the robot is able to complete the task also in such unseen scenario. And so they show that with these additional data, they were able to improve the generalizability of the system. But the problem is that so these models are still struggling with long horizon tasks and generally tasks that require high accuracy. So in order to overcome these limitations, so again, like physical intelligence, like very recently, they released this new approach which combines VLAs with reinforcement learning. And they released this model called RL token, which again, they still use the usual VLA mixture of transformer architecture. But what they did is that after pre-training the VLA, they also train a small what they call RL token, which is trained from an autoencoder. And this RL token is able to sort of encode so information from the VLM because of this autoencoding mechanism. And then once this RL token is trained, so the RL token is fed into an actor-critic network and is trained in traditional RL setting to then improve the outcome of the VLA. So basically, this is, it's a bit blurred, but this is their architecture. So you have the original VLA, which is pre-trained, then they train this RL token. Then the RL token goes into the critic and actor, and this critic and actor, they're trained directly in the real life, from real rollout in order to, let's say, improve the action prediction from the action expert of the VLA. And in this case, they show that, for instance, in this example, so the robot is able to complete this task of putting, this wire inside this hole, which actually it requires a lot of dexterity and precision. And they show that, with this RL integration into the VLA, so they were able to increase much more the throughput of tasks. So the speed to complete the task was improved much more. And also they were able to also improve the success rate. So they had much higher success rate compared to not using, RL. So then, another important factor, which has been quite significant recently in the field of robotics, has been this concept of word models and video generative models. So again, like in the general AI community, after LLMs and so on, so people started investigating how to generate videos, like there was, for instance, diffusions for generating images, and then they moved on to generating videos. And the idea of generating videos is that because from videos, generally, the model is able to understand the underlying physics of the word, ideally. And is that for sure a long time and space. But then because of these capabilities of video generative models and word models, so people start integrating these architectures also in robotics. So for action generation, so not only for generating videos, but actually to generate robot actions. And there have been three main sort of architecture types, which have been quite popular. So one is this one, like on the left, which is called inverse dynamics based. So basically you have two main models. One is this video generative model, and the other one is the action model. So basically, first, the video generative model generates a sequence of images based on the text and the input image. And then given this sequence of images, they are passed to the action model, which predicts action based on two consecutive images. So that's why it's called inverse dynamics, because given the current image and the next image, so this model predicts the action, which is causing the transformation from initial image to the current image. The second architecture is this one called mixture of transformers, similar to the Pi0 VLA architecture, but in this case, it's like there are three transformers. So there's the standard, let's say, VLM understanding expert, which takes the current image and the text to understand the human interaction, understand the scene, and so on. Then there is the video generative model, so which again, given the current image, generates future images. And then there's the action expert that takes pure noise and generates action based on diffusion or generative flow matching. And these three models, they are separate, but still they share some common attention. So to learn from tokens of each transformer part. And then there's this other approach, which was presented by NVIDIA, which is a joint video action model. So in this case, is that they use only one single video generative model, but this model is fine-tuned to take as input both images and to generate both images and robot action directly. But they just use one single video generative model. And so, and as I show here in this example, so this is as I mentioned, so the example from Dream Zero from NVIDIA, and actually their architecture is based on the video showed before, so Dream Dojo which is their video generative model, and they show that by integrating the single video generative model to be able to predict actions, they show that their model is much more capable than standard VLA. So, for instance, Groot it's brute or Python 0, they're just standard VLAs that they don't use videos, whereas DRIN 0 is their video action model. And as you see here, so this model is able to, generate actions of the robot, but also generate videos. So these videos down here show how the model predicts the robot should act. And so it predicts, like some future frames, then the robot itself is going to go through. And as I mentioned, so these video generating models, I mean, are quite good because ideally, so they learn more the physics of the system. And they're also quite good because they can be used to generate more synthetic data, which is a major problem actually for robotics, for data collection. But the thing is that, as I mentioned, so they require a lot of computational resources, a lot of data. So, and another important sort of let's say innovation that happened in robotics is this thing of, for sure, humanoids have become very popular recently, but humanoids have been going on for quite some time. But recently there have been this new breakthrough on how to train humanoids to mimic and act like humans. So nowadays there are like approaches that allow just very easily from a simple video to train policies to make robots move completely like human. Again, this is like some word from NVIDIA. So you just have a video of a human, and then you are able to make the robot move just like the human. And again, recently NVIDIA released this new other approach, which is called Sonic, which is a whole body controller where you can command any sort of motion to the robot, and the robot is able to to track these motions and um, and follow the commands, which can come from joystick or a VLA and so on. But again, this model is trained on many frames, so 100 million frames, and it's quite big model. But it's this integration of whole body control is also very important for the actually broader concept of whole body local manipulation. Because basically, I mean, for now, VLAs have mostly been trained, or most of the demonstrations that we've seen using VLAs, they're generally on robotic arms. But robotic arms, they're a fixed base. But for ideally in future, especially if you want to deploy humanoids, humanoids, they need to go around and walk and so on. So most likely you saw this video from Figure AI. So where this humanoid that goes, inside the room, uh, picks up some glasses or whatever. So it needs to clean the room. And you see it needs to squat, it needs to move around and so on. So because of what I showed you before, so nowadays there's also these policies where for whole body control, which make much easier to train humanoids to behave like humans and maintain balance and so on. So nowadays there's also this additional new trend of having a full sort of stack pipeline where you have both the brain coming from the VLA, and then you have the whole body control coming from these low-level body controllers. So this is a bit like the most recent trend, especially for humanoid robotics and any logo manipulation task, where the VLA or whatever any other video generative model acts sort of as the big brain and a high-level reasoner, which sends high-level commands to a lower-level controller. And then the lower-level controller is like responsible for the navigation and the more the navigation around and eventually the fine-grained manipulation. So the thing is that so even though there have been a lot of progress in robotics in this past, especially 4 or 5 years, there are still quite some limitations and challenges to face. So first of all, safety. So for now, all these VLAs or whole body control policies or whatever, generally they are trained on a specific task. And so they're trained for the robot to excel only on that specific task, but they oftentimes neglect whatever happens around. So maybe you've seen already some videos of some robot dancing and then slapping people nearby or kicking people nearby because they're not, their goal is just to dance. So they just they're not aware of what happens around them. Another another big limitation for now is the full dexterity. So most of these VLAs, they are trained for and on robots with 2-finger parallel grippers. There are some more works which are trying to expand to dexterous hands, but the full human dexterity is still quite hard. And the other thing is for sure training accessibility. So generally, data is still quite a big issue for training visual language action models or eventually even video generative models. And then, as I mentioned, so the other big issue is mostly about long horizon tasks. So generally, VLAs or video generated models, they're good, but at solving tasks which are not that long. But if you want the robot to navigate around, do tasks for minutes or even hours continuously, that's still a major limitation, which requires memory, planning, eventually, recovery. So, and as I mentioned, so one of the main issues for VLAs, vision, and visual generative models and so on, so is data collection. So nowadays, there's a lot of effort on teleoperation, but teleoperation, it requires humans to be quite expert in, teleoperating robots. So, some approaches have come up. So one of the main approach which has recently been used is this one of UMI, so Universal Manipulation Interface, which is basically, so it's a special gripper which both the human and the robot can use. So basically the human collects data by wearing this gripper, and then this data is collected and then it's used to train the robot. And then this gripper is also attached to the robot. And so in this case, there's much less difficulty due to cross-embodiment. So this is one of the major approaches that people have been exploring, to collect data and train robot policies. And then the other major research direction is about actually directly leveraging human videos, because for sure, we as human, we do so many tasks like every day. There's a lot of videos online of human performing tasks. So this is another big point for how to leverage human data to train these robot policies. And then the other approach would be ideally using synthetic data. So as I mentioned before, these video generative models are quite good also at generating synthetic data. And so ideally, they can be used for training also these policies. So finally, so just some overview about future direction. So as I mentioned, like especially in these past 4 years, the evolution of robotics and embodied AI has been very, very exponential, and it was reflected also by lots of funding in the field. So nowadays there are so many companies that they were just born maybe 1 or 2 years ago, and they're worth billions of US dollars. And generally, there's two major sort of business model. So some of them are mostly focusing on training unified policies like to act as a whole robot brain, so which can be used on many different robots. And other of them are actually more focused on hardware and like generating also data to be used by other companies to train their models. But the thing is, also, as I mentioned before, so even though there have been these major trends, so there are still some limitation things to overcome. For sure, as I mentioned, so VLAs and video generated models and word action models are still quite big. So generally, to have a good model, there are maybe around 3 billion parameters and so on. So it's hard for these models to run on devices. So one trend would be to compress these VLAs to be able to run on edge devices. Another big focus for now is to augment VLAs with RL, which, as I mentioned before, it's able to improve generalizability, robustness, and also be able to perform high dexterity tasks. And then nowadays, there's a bit more this shift of moving from VLAs to word action models and video action models. Then I guess more focus would be on cross-embodiment policies. So generally, eventually you can just train your policy on one model, but then this policy will be able to be transferred directly on many other robots. Another focus, as I mentioned, is also this thing of learning from human videos, because there's so many data, of us doing tasks. And one other big aspect is this thing of user-friendly fine tuning. So for now, again, especially in future, if you want to have a robot as our companions, right? So maybe I want to tune the robot to do a task, because I want it to do a specific task. But for now, I mean, if I want to tune a model, like a robot or a policy, I still need to be sort of expert in the field. So most likely in the future, there will be much more user-friendly approaches, to fine-tune these policies and teach robots. And two other big technical limitations for now are also this thing of integrating touch and force sensing. So for now, these VLAs generally they only they're only based on images and text, so they don't use any force feedback. But this is like still a major limitation, I would say. But people are trying to um, come out with some solutions. And as I mentioned, the long horizon tasks, so that include navigation, memory, and also planning. And then in future, most likely we will see more human dexterity. As mentioned before, one of the main problems is still safety for these VLAs and robotics. So before, I guess robots will be our companions, there needs to be a bit more safety regulations. And then ideally, I guess in a maybe even further future, we will be able to see robots that they are able to improve on them by themselves. So maybe just looking on searching online for how to solve a task and then learning directly by themselves. So this is my talk for today. As I mentioned, so it was more or less like a high level review of how robotics and embodied AI has changed over time. And if you're interested, I mean, I have this blog where I just post some summaries about robot research. So if you're interested, you can just follow and take a look. So that's it. Thanks a lot.
Thank you so much, Dr. Francesco. I hope you can still join this online meeting, right? Because after this, we will invite the second speaker, and then after second speaker speech, we will have a Q&A section. Is that okay for you?
I think I can for a little bit longer. Yes.
Okay. Thank you so much, Dr. Francesco.
Thanks.
Very, very beautiful presentation from you. Thank you. Now I would like to move on to the second speaker. Let me in charge. First of all, I would like to invite Professor Haryo to the stage. And then let me introduce briefly about the Professor Haryo. Professor Haryo is the faculty member at the ITS Surabaya since 1995. It's very, very long journey of lecturing. Okay. And Professor Haryo was appointed as 220th ITS professor in coastal protection structure. He completed his undergraduate study at Gadjah Mada University, then pursue his Master of Engineering at Memorial University of Newfoundland in Canada, and then he's finished his doctoral degree at Queen's University in Kingston, Ontario. He is inventor of Hexarif, an environmentally friendly artificial reef submerged breakwater that has been deployed in Madura, Raja Ampat, and Manado. Okay. He also contributed to the development of concrete armor unit or CAU, including BPPT lock. I think BPT now it's become merged with BRIN. Professor Haryo also invented BRIN lock and BRIN pot. And now he will give a talk about the integration of robotic and AI into coastal engineering, especially for monitoring the underwater construction, I think, for the installment and monitoring the artificial reef. Without the further delay, I would like to give the time for Professor Haryo. Please, time is yours.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, Bapak Ibu, everybody in this room or also online. Yes, first of all, yeah, I'd like to thank you for the invitation. I think all of you maybe think about that I'm in the wrong room, yeah, because if you listen from the introduction, actually I'm a coastal engineer. I'm graduated from civil engineering from Gajah Mada University, and then I work also in the ITS, Institut Teknologi 10 November, on the Ocean Engineering Department, Faculty of Marine Technology. But the ocean actually, so that's when I was invited in this conference, and I have to think that what is part of my research is related with this conference. Yeah, fortunately I have. It's about, I will talk later, but now maybe a little bit I will explain about the ITS and also what kind of research in ITS related with this conference, the mechanical electronics, robotics, AI, and etc. So yes, we have a booth in the front. Also, I also teachers lectures in the School of Interdisciplinary Management and Technology. I came here with Dr. Dinariana. He's the head of the doctoral program in School of Interdisciplinary Management and Technology. So that's why the interdisciplinary technology, that's what I like to talk about. So what is the interdisciplinary between the mechatronics, AI, and what is the my subject, the coastal and ocean engineering. I think yesterday we already learned or maybe watched the presentation by Dr. Milford. He also a little bit in the beginning, in the end of this presentation, he showed us about the autonomous underwater vehicles. We also seen about the drone, something like that. But most of us, maybe not many familiar that we also in ITS have already have a research about the autonomous ship, autonomous boat, also autonomous for the survey and the ocean also. But yes, maybe next slide. So yeah, we have about 9 faculties in ITS. The youngest one, the faculties, is the medicine and health. This is also related with some AI and robotics. Also, we have a biomedicine, biomedical engineering also. So, School of Interdisciplinary Management and Technology, and not only the faculties. The next slide is also about the research center. We have there are 2 directorates in ITS: Director Research and Community Service, which have 12 study centers. Some of them related with this conference also, these topics. But we have also study center on artificial intelligence and digital technology. We have also study center on defense technology. One of the researchers, maybe you already have known about Professor Subhan. He also has a strong research in robotics and combined the defense technology with robotics. He got the funding from the UK when he did his PhD. Now he's developed that also. So the drone, the technology is also have their place in this study center. Beside the study center, we also have the next slide is from the other directorates below the vice rector of the research and innovation. We have a director innovation and science techno part. This is more innovation, not only study, but it's more innovation related with industries. State here in the red colors here, the cluster of ICT and robotics. We also have the cluster of ICT. There are 2 center of excellence there, Mechatronics and Industrial Automation, Science and Technology. Also the Center of Excellence on Artificial Intelligence and healthcare society. So this is also have a place in ITS. The other two clusters that also related with these topics is Center of Excellence on Automotive Control System, and also the Pak Dinar is also a member of this cluster, the Center of Excellence on Ship Safety and Science and Technology. So hopefully maybe the next ICMS we can have in Surabaya, Pak Sabdo, or maybe I don't know whether, because we are strong in the research on the ICT, robotics, and etc. Maybe already know also that robotics also is like in ITS for our undergraduate students also is also the part of their activities, student activities. Okay, that's for introduction about ITS. For those who knows, maybe also we have a booth from outside that we also have the program. It's called PPI, the Professional Engineering Professional Program. So after for the undergraduate student, or maybe everybody who already graduate from the engineering. So if you want to work on the professional, then you have to take the professional program, professional engineering program. So we also in ITS has that program also. It could be online. You don't have to come to Surabaya. The program is offered online only for 6 semester. 6 months, 1 semester for those who already has a experience. But for those for the new graduates, takes 2 semester or one year. Okay, so maybe now I will talk about the topics. My part of my research that may be related. I work this with some colleagues from the Mechatronics. Yeah. So as we know that we have Indonesia, we are an archipelagic country. We have so many islands. So I think we have to put some concern, or we have to take part on the development of the countries, especially that we already have islands, spread people, so many ports. Because I came from I'm in my department, I'm the head of the ports and infrastructure laboratory. So mostly I work on the like a civil engineer, yeah, because I'm graduated from civil engineering. So how to develop ports, how to develop the protection, coastal protection. Maybe if you go to the ports, you go to the ocean, the beach, that we will think how to, like maybe these days you will heard maybe read about the giant seawall. So something like that. So that's our actually that's a part of our study or our research. So do we need a giant seawall or not? Something like that, yes. But ports, there are some belongs to Pelindo, belongs to some other companies. Also, there's also ports, fishing ports that we already saw about spread from the north and south part or east and west part of Indonesia. So wide and so many ports, kind of ports in Indonesia. Not only this, we have our military ports. We have also the marine and gas, yeah, for the gas, oil and gas port, something like, and some also for the between island. We have also the ferry port for the ferry. So many ports. Also, all of them need electronics, mechanics, something like that. So, okay. Next slide. So, in some ports, to create the area where the ship can berth and the ship can stay on the port, we have to protect the area with the structures is called breakwater, seawall. So that's why it's called giant seawall, because it's so high, it's so big. Yeah, but this is a typical cross section of the breakwater. So maybe all of you knows about, maybe if you go to some ports, we see about the tetrapod in the left side. Tetrapod is very common in Indonesia. It's the armor, concrete armor unit, CAU, is the function is to protect the structure. You see here, the yellow concrete armor unit from the table here. It was invented in 1942. That's the concrete armor unit nowadays still used. But then there are so many inventions about the concrete armor units, as you see here, from 1968, etc., until the current that I put in red font here. We are so proud that also Indonesia have some invention of our own concrete armor unit. So most of them are getting better and better. If you see here, Tetramin 4, there are only 4 legs. But if you see here, some of the new or the modern concrete armor unit, there are 6 legs. It means that they are more connected, they are more stronger, they can hold each other. So they will hold the wave because it will protect the structure and also the area behind the breakwater. So the wave can reduce and the area behind the breakwater is calm. There's no wave. The ship can burst there. Maybe people can have some activities. Coastal protection structures need actually depend on the wave. Wave, you need the higher or the bigger or the heavier concrete armor unit. So, but the modern concrete armor unit, we don't need to make it heavier because they have so many leg or they have many arm, 6 or comparing with tetrapods, which is only 4. So it's not to be heavy, but because they have so many legs, they can connect each other. Okay, so that's the introduction. So we need concrete armor unit to protect the shoreline and protect armoring the coastal structure. There are 3 layers of the structures. So core layer, secondary layer, and the last is the concrete armor unit. So now there's the problem. How big is the concrete armor unit? Maybe the next slide. This is the example of the construction that we involved in Denpasar, in Sanur. It's a port for the tourism. If you go to Nusa Penida Island, before the port is developed, we have to go to the water to go by boat or to go to the island. Now they build this port, and as I said before, that the port needs a breakwater. This is a typical construction. This is they use a PPT lock. Before that, they use about 10 tons of tetrapod. Tetrapod is the old concrete armor. Imagine it's a 10 ton of tetrapod and very heavy, and it's so expensive. Yeah. So then we propose that instead of using tetrapod, what if we use our own invention, Indonesian invention? It's called PPT lock. At that time, it's not there are BRIN. When the PPT lock was invented, is still called PPT, not BRIN. So our proposal is accepted, and then the government is agreed. This is belong to the government of the Ministry of the Transport. The government agreed to convert, not use tetrapod, 10 tons tetrapod, but only 1/3 of the size of the tetrapod, only 3.6 ton of PPT lock. It's still quite heavy. So 3.6 ton PPT lock. So then, as we can see here, that the PPT lock they cast in the area, they made on the vicinity of the the area, the construction project, because it's so heavy. Because if we make in the factory, maybe it takes it takes longer time. So they cast it, they made it close to the project. But it's still heavy. If you can see here, the small people there comparing with the PPPT logs. The height is about 1.6 meter. So maybe, yeah, as high as myself, 1.6, 1. So it's quite high and quite heavy, 3.6 tons. So we need the crane, or we need excavator to deploy or to drop the construction. Then, like I said before, this concrete armors will work together if they can connect each other. If we put all the position, the problem is it is difficult in the field if we can connect it like playing Lego or playing puzzle. Yeah, because the construction process, they just use a crane and drop it. Yeah, so it is still good, but it's not work properly. So most all of the concrete armor units just drop it. They don't try to connect it or push it. So that's the problem. Yeah, that's the problem. Even though it is still work. Yeah, but if we can arrange the concrete armor unit connected each other, it will be like Lego or a puzzle. It will connect it and it will work together and will be strong. Yeah. So then, next slide. To make sure that all units are connected, usually there is a scuba diver. They go inspect or maybe give instruction how to put the concrete armor unit underwater. If it's above the water, maybe it's easier because we can see, but it's underwater, it's difficult because we have to have some scuba divers to make sure that all is connected. Still, also, it's not really a success because of usually it's very difficult or very dangerous for the scuba diver. You know that in the ocean there are some currents, there's a wave. Also, the weather is not good sometimes, so it's difficult. Maybe work underwater, especially if the highest wave. So there is physical limits. Scuba divers also cannot work at the long time. What if in the night the project has to be finished, but at the night what they cannot work in the night, scuba diver, because it's limited light. There is no light. So that's the problem. Yeah. So we need to put a camera. So we think that what if we give a camera? This is not, I mean, this is just the idea. We have not yet in Indonesia. So that's why I invite maybe everybody or maybe Bapak Ibu here, maybe interested in this research, we can make it together. So we can make a camera. So the camera, maybe the next slide, we can monitor. Yeah. So like we see in the previous picture, the operator of the excavator, the operator of the crane, they will know how to put the concrete armor unit. On the right side, usually they give like a clamp. In the right side here, there's the underwater. They have to size system, underwater system, and the above the water system. In the underwater system, there is a clamp. Yeah, there's a clamp that can hold the tetrapod or concrete armor unit. So the clamp will arrange how to make it properly. The place the concrete armor unit is properly, how it's connected. If we know the pictures, then sorry, thank you. Yes, so it's clamped like this. We have the tetrapod underwater here, and there is a clamp. There is a camera here also. We put camera here, so we can have the picture, the visual view of the tetrapod or a concrete armor unit. So from here above the water, the picture here will be sent, will be analyzed. This is not my, this is the colleague, our colleague has put some analysis about the image analysis, maybe with JSON or with others. Initially, we use Raspberry Pi, and then later on we use JSON. So to analyze the pictures, and then after that, shows to the operator, to the excavator operator, so they can arrange the placement of the concrete armor unit properly. So that's the idea. So this is what we did so far. So maybe in the next slide. So we try to automate the detection, detect how the concrete armor, the position, whether it's already good or not. We have to develop the capable tracking the position, whether this is properly placed, or maybe we have to little bit move it. And also because it's underwater, usually the underwater is not clear. There are some silt, sediment, also some organics in the water. So the water is turbid, it's a murky or turbid, not very clear. So we have to improve the image of the underwater camera from the underwater camera. So the overcome the turbid water and low visibility condition. So we have to pre-process the image. And then after that, so we have to evaluate the model, the light weight, the model from the image. Then we have to make sure that what the software or the application that we will put in the excavator or in the operator. Yeah. So they will know how to put, because not only a visual image, but they also have to analyze the visual image from the room of the operator. Next. So the problem is the turbid water. That's the obstacle of the image. Low light, the suspended particles, the sediments, maybe some of the organic material reduce the visibility of the image. And also that's why we have to enhance the image and restore the color. So we have tried to analyze with the three of this histogram equalization, the contrast limit adaptive histogram equalization, and also MSRCR. So we analyze that, what is the best method, restoration color between three of this by image quality analysis, whether it's underwater color image quality, and then also the underwater image quality management. So from some of this, the HE is considering it's better than other two. So in the next step, please next slide, we will use it for analysis of the image. So this is a typical placement of the system. So this is the excavator arm. In the excavator arm, there is some, maybe we have clamp, or maybe like not only clamp, but we have some ropes to hang the concrete armor unit. But we put some camera here. There are two cameras because we need three-dimensional images. So the first camera, two camera, and then from the camera here, then we will know, it will take the pictures, what is the underwater position of the concrete armor units it's look like. So we don't have a chance to develop the system, but it's still in the laboratory, but not put in the real excavator. Next slide. Then we go to the next step, is that we need to analyze the image, the candidate. We use, there are three. Now at the time we still use a YOLO 7 version. Now it's maybe higher version, and we compare the result. Which one is better? Maybe the next slide is the comparing the result. What if we use a single object? What if there's multiple object? Still, is this in the laboratory experiment? This is a model of the tetrapod. But from the computational performance, because we need to send the image, the average frame per second is better if we use the YOLO 7 version, comparing with the others, whether it's in clear water or turbid water. So But also we can see also that to identify because in the real project we don't not only put one single tetrapod but several, but we have to make sure that all the object is captured by the system. So by comparing this, we can see also here whether it's from YOLO 3, 4, version 3, 4, and 7. For the clear water, for sure is good. The percentage also the confidence score is highest for the clear water because it's clear. But on the turbid water, there's some significant increase comparing with other version of the YOLO. The 7 version is increased from 60% to 80%, which is 20% increase. So it's so far our conclusion is I don't know because at the time and on 2024 is 2 years ago. This is our paper. So YOLO 7 is better. Maybe now we have YOLO 7, YOLO 11, 10 or better. Maybe has the better process. So that's the idea. Still, we invite the collaboration. We invite for the research together to make this system or to make this equipment is available for the contractors, for those who work in the coastal project, underwater project. So it will help also reduce the danger or for the diver, scuba diver. So it will saving times, reduce costs, and protecting human lives from the high risk underwater labor. So I think that's my presentation, Pak Sabdo. I hope I can satisfy your all of your inquiries. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Haryo. I think it's very interesting topics, right? When the robotic or computer vision meet can solve what really happen in the real environment. Okay, now I would like to invite the audience, both online or offline. If you have any question to our speakers today, maybe for Professor Haryo or for Dr. Francesco, please let me know. Online, please check the online. Hello, online audience. If you have any question, please raise your hand. We have 2 speakers today, and they already deliver very insightful presentation. I hope. Okay. Maybe. Oh, okay. Dr. Slamet. Maybe ada ini. Okay.
Thank you. My name is Slamet. I want to ask to Dr. Francisco.
Yeah, Dr. Francisco.
Francisco, okay. Can you hear me?
Yes.
Okay, thank you. So actually our team work on AI. We engage in smart farming, okay? So this smart farming actually what to say? It's like have its own timing, maybe 10 years ago. So, but after we make our research, we deal with many problems in real world. In that day, we see in developed country, there's so many applications But after we try to implement in our developing countries in Indonesia, there is some problem in the real world because so many things should be considered. How do you think about the robotic itself? Because it's very interesting now, today. What field would be fit for developing countries to implement the robotic, but non-military? So for military, maybe they have their own budget, something like that. But when we deal with, for example, smart farming, when we implement this to the real world, there's so many obstacles in budget. The revenue stream, they will calculate it, and in the end, it's very difficult to implement. Do you think in this humanoid or maybe another robotic, what field should we focus in developing countries? Thank you.
Thanks for the question. I wish I knew the answer. Unfortunately, I don't know the answer. But in terms of, let's say, form factor, so shape factor, I mean, I don't think humanoid is the answer to everything. So, humanoids are good for if you need to work around, in like unstructured environments, with many steps and such. But it depends, not every environment needs legs, right? So you may have more appropriate sort of, robot types, let's say. But I think that the recent trends, nowadays with these, VLAs or reasoning models and such, is that I think they have two, the good capabilities that they have is that they're able to understand, okay, I mean, the human instruction, but also understand environment better than before. Because even before, as you mentioned, maybe, a few years ago, even if you wanted to do, I saw some tasks where there were these robots, picking strawberries, right? But in that case, you still had to do something a bit more sort of programmed because you had to have computer vision to detect strawberries, I don't know, like some motion policy to go and pick the strawberry. Then if something failed, I mean, I don't know what sort of implementation was there, to recover this thing. Nowadays, AI is becoming a bit more. I mean, there's still work to do, but at least it's becoming more smart from this perspective. So, AI is able to the strawberry dropped. So, I mean, at least understand that the strawberry dropped. So it can understand eventually how to change the action of the robot in order to, recover from some failures, let's say. So I would say nowadays AI is becoming, as I said, smarter to solve some problems. There's still work to do. It's able eventually to be able to integrate in more difficult environments, in terms of changing of lightings and so on, right? So before, I guess you can see also with autonomous driving. So autonomous driving, like one of the main issues that you have the car needs to drive in many different places and so many different conditions, right? Dark, sunny, rain, and so on. And nowadays, again, these models, because they are trained on so much data, they can still handle this situation, better than before. There's still for sure limitations. So I guess that, I mean, as I said, so these new called, as I said, VLAs, video generated models or whatever, they are better than before at understanding humans, understanding when things go wrong, sort of replanning, being a bit more robust under different situations. This is for sure. Then, I mean, the application itself, I'm not sure exactly. As I wish I knew the answer because, maybe it would make me richer. But for now, the application wise, I think it's still a bit hard. And for sure, it's very still quite application specific, let's say. Because even in farming, maybe you want to have, data collected just in a specific farming scenario, which would make your model better, for that task. So I guess you still need some specificity for where you want your robot to be deployed. And then, of course, in terms of hardware, so in terms of shape, same. I mean, I don't think humanoids will solve every task. I think, it depends on which application you want, right? So if you want mobile robot, leg with wheels, all these things, yeah.
Okay. I hope that satisfies the okay. And any other question from the audience in here or the online participant? Okay, yeah.
Ya, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
My name is Arifa Fitria. I'm from National Research and Innovation Agency. I would like to ask Prof. Haryo Dwito Armono. My question is, I would like to ask regarding the real-time performance of the system. What is the approximate latency of the real-time monitoring system from video capture to object detection result? Okay, thank you.
Thank you, Bu Fitria. It is I think it's on the paper, Bu Fitria. I think on the papers. I don't remember because it's a long 2 hours ago, but it's very short time. So maybe I don't know because it's beyond my expertise. But our colleagues from the Dr. Payumata has said, but I think it's very quick. So that's why we choose YOLO 7 because it's the average process is very quick. So it's like the real time. There's no lags of the pictures of the image. So I don't know. Is that answer your question? But in detail, you can see, or maybe I can send you the papers. Yeah, it's on the papers. Yeah, I don't remember what's the exact time, but it's very quick.
Thank you very much, Professor. Any other question from the audience? Maybe I would like to ask one question for Dr. Francisco. As you mentioned that fine-tune the model or train the model is very expensive. Do you have some suggestion for student how to start the research in your area, because it's hard for student to start the research, like if we don't have any good infrastructure, right? Like you mentioned in your presentation, because it's quite expensive. Do you have any suggestion? Maybe they will start not from that, but what is the starting point to start? Okay.
Sure. I mean, I guess it's a very important question. Because even though I work for industry, but some things we cannot implement because if you want to train video models, you really need, I don't know, like so many H100 GPUs and such. So I think, one good thing is that for sure in these recent years there's been a lot of more open source resources that makes things much easier. So, putting aside the computational cost, but in terms of, architecture, coding, so models and so on. So there's many open source projects that allow, to play with models and such. And one very popular one, it's I don't know if you know, it's like from Hugging Face. There's a library called Le Robot. So over there, you have model policies, which with some of the latest policies, VLA policies. You have all the data infrastructure for converting your data, and then all the training pipelines. For sure, yeah. Then as you mentioned, it comes down to how many GPUs you can use. For sure, you can simplify things a bit because you can start from simple tasks where you don't need that much data. You can fine tune the models, only using like those parameter efficient approaches like LoRa or so on, which don't require to train the whole model, but just some parameters. But as you mentioned, for sure, if you want to do more complex tasks, or if you want to tune whole models, unfortunately, it's quite costly. And I mean, I'm experiencing, both, from my job, but also from my personal projects. And whenever I want to train a model on my own laptop, actually, I cannot. So either I go online, on those platforms that you can rent GPUs, but it's not cheap at all, or otherwise, as I mentioned, so it requires a lot of money and computational power, yes. So I would say start simple, at least, some simple tasks are fine. You don't need to have, these big models that generalize to everything. So at least for some sort of small projects, I guess, you can do at home. But when you want to move to broader things, then yeah, you need somebody to to help from economic perspective, yeah.
Yeah, thank you very much, Dr. Francesco. I would like to remind you that Professor Haryo and team is open to collaborate with you guys. If you have something, you can reach Professor Haryo for collaboration, of course. And maybe BRIN also will reach for long-term.
Oh, can you hear me?
Yeah, now we can hear
So,
you.
I personally am, but company-wise, it's a bit hard. So it's not me to make the decision. But so yeah, it's something we need to discuss. But yeah, like for company policies in terms of collaboration.
Yeah, sure, sure. Much for your attention. Thank you, Dr. Francesco, for joining us.
Thank you for the
We
invitation.
can invite you for another
Yeah.
event, right? It's okay. Okay, thank you very much. Thank you
Bye-bye.
very much, Mario. We very happy to have you here, and Dr. Francesco. Okay. And now I would like to close this session. I would like to thank all of you, and Assalamualaikum warahmatullahi wabarakatuh.
The afternoon keynote speakers, Dr. Francisco Cursi and Professor R. Haryo Dwi Armo, for sharing your remarkable insight with us. Please applause. Our sincere appreciation to Dr. Sabdo Utomo for moderating such an engaging and full plenary session. Express our deepest appreciation, we would like to present a token of appreciation to Professor Haryo Armo.
May we invite the representative of Chairman of ICSMech 2026, Mr. Adit, to present the plaque to Professor Haryo. Please give a warm and a round of applause once more. Thank you, Professor Haryo and Dr. Sabdo Utomo. Please kindly return to your seat. Ladies and gentlemen, Our afternoon parallel session are now underway. On-site rooms are 1, which in Ballroom 1, and R2, which in Ballroom 2, are hosting presentation on autonomous vehicle and smart machine and intelligence instrumentation and embedded systems. Virtual room V1, V2, and V3 cover information system for mechatronics, robotics, perception, and biomechatronic system, and autonomous vehicle and biomechatronic systems.
All presenters have 12 minutes for their presentation and 3 minutes for Q&A. Let's make this final session as great as everything we've seen.
Recording in